Hello! In this video we are going to look at one of two types of improper integrals. An improper integral could have a vertical asymptote or a horizontal asymptote, and in this video we'll consider ones that have vertical asymptotes. So let's take this as an example to start with, and let's pretend that I don't notice that there is a vertical asymptote when x is 0. Okay, that is when the value of x is 0, the integrand here is undefined. So we can't actually carry out this integral using normal methods, but let's see what happens if we try. So this is obviously going to be equal to x to the minus 2. So when I integrate that, that's going to be minus x to the minus 1. And that's going to be evaluated between x values of minus 1 and 2. And then I sub in my limits. So I get minus a half by plugging in x is 2. And then when I plug in x is minus 1, I'm going to get minus negative minus 1, so that's minus 1 altogether. And I get that the answer then is minus 3/2. So on the surface of it, it looks like that this integral equals minus 3/2, and at a quick glance, it doesn't look like there's an issue. However, let's just think quickly about what this curve actually looks like, because the whole of the curve is above the x-axis. Looks like this, which means that this area here, when you evaluate the integral between minus 1 and 2, should have come out to be a positive number. Yet we've got negative 3/2. So we know just from that that something must have gone wrong. So how do we decide what the value of this integral is if we can find it? Well, and that's where this video comes in. So when you're dealing with an improper integral that has a vertical asymptote, so in this case it's when x is 0, then what we need to do is we need to split the integral up into two pieces if the asymptote is in the middle, like it is here. And we're going to take a limit as a tends to 0 of the integral from minus 1 to a of x to the minus 2 dx. And then we're going to do the other half. So this integral here is the integral from minus 1 to 0, because we're going to take a to 0. That's going to be this area here. And then we're going to go from 0 up to 2. So we're going to do the same thing again. But this time the limit as a tends to 0 of the integral from a to 2 of x to the minus 2 dx. Okay, so that's what we do. This is the notation you need to use. And if you wrote that, then that would be correct for this course. However, to be mathematically correct, we should really put a little superscript negative here and a little superscript positive here, just to emphasize that we are approaching the number 0 from below. So what we're going to do is we're going to take the value of this integral, and then we're going to take the value of a up to 0. So it's starting something lower than 0, and then we're going to see what happens to this integral as it approaches 0 from below. And the same thing here, but this time we're going to take a small positive number and then take a to 0 from above. So it should have little superscripts, negative and positive, but you wouldn't lose marks if you didn't do that for the maths course. Okay, so let's evaluate this. So just keeping the limit notation out the front for now. So limit as a tends to 0 from below of minus x to the minus 1 between minus 1 and a, plus the limit as a tends to 0 from above of minus x to the minus 1 between a and 2. And now we sub in our limits, just as we would normally. So limit as a tends to 0 from below of minus 1 over a. And when I plug in minus 1 into there, I'm going to get minus 1 altogether, because there's 3 negatives. And then plus the limit as a tends to 0 from above of minus a half plus 1 over a. Okay. Now, the problem with this is when I try and plug in a as 0 into this expression here for a, then I end up trying to divide by 0. So I can't divide by 0, that's not allowed. Same thing occurs here, I can't divide by 0. Therefore, this integral does not exist. Okay, i.e. the area is infinite. Or we could say the integral diverges. So this area here, between -1 and 2, and the x-axis and the curve, that is an infinite area. And we can kind of see where the naive -3 halves came out, because if we look at that, you can kind of cancel the 1 over a with the -1 over a, and that's kind of what's happened in the incorrect case over here. But in this particular case, you can't actually cancel those because 1 over a doesn't equal -1 over a when a is 0. Okay, and that was the issue. Okay, so this area, this integral is infinite, it's divergent, we can't do it. However, that's not the case for all of them. Sometimes we can carry out an integral that has an asymptote, and it is convergent. So let's have a look at this example. This one has an asymptote when x is 1, because I'll be dividing by 0 to the 2/3, which is 0. So that's going to give me a vertical asymptote. So I'm going to split this integral up into 2 pieces, just like before. So this is going to be equal to the limit as a tends to the number 1 from below, because the number 1 is the issue this time, of the integral from 0 to 1 of x minus 3 to the negative 2/3 dx. And then I need to add the other piece, which is the limit as a tends to 1 from above of the integral, sorry, that should have been an a there, of a to 4 of x minus 1 to the minus 2/3 dx. Okay, evaluating those, you get the limit as a tends to 1 from below of, add 1 to the power divided by new power, so it's going to be 3 into x minus 1 to the power of a third. That's evaluated between 0 and a. And I've got enclosed bracket, and then plus the limit as a tends to 1 from above of the same thing, 3 into x minus 1 to the third, but this time between a and 4. Okay. Plug in our upper and lower limits. So it's going to be equal to the limit as a tends to 1 from below of, upper limit in there is 3 times the cube root of a minus 1. Plug in x is 0, I'm going to get minus 1 cube rooted, which is minus 1, times 3, but I'm subtracting it, so it's going to be plus 3. And then do the same thing here. That's the limit as a tends to 1 from above of 3 times the cube root of 3. And then plug in a is 1, it's going to be subtract 3 times the cube root of a minus 1. Okay, so that's what we get. Now, however, when we plug in a is 1, this isn't going to blow up to infinity, this is going to converge to 0. And that's because if I plug in 1 into there for a, I'm going to get the cube root of 1 minus 1, which is 0. So this is now going to tend to 0. As is this. This is now going to tend to 0. That was different to the previous case. Last time it blew up. This time it's collapsing down to nothing. So when I take the limit as a tends to 1 of this expression, that's going to disappear and I'm left with the number 3. And when I take the limit as a tends to 1 of this expression, that's going to disappear and I'm left with this, which is plus 3 times the cube root of 3. And that's the answer. So, even though the physical area here has got an infinite perimeter, because it's got a vertical asymptote, the area enclosed between this curve and the x-axis and the vertical lines, x is 0 and 4, is a finite area. Okay, and it's equal to 3 plus 3 cube root 3. I've got 2 more examples. I'm going to go through these 2 a little bit more quickly. So here's example number 3. We know the tan graph. You should know that very well from A-level maths. It looks like this between 0 and pi on 2, and we have a vertical asymptote here. So what we're going to attempt to do with this question is we're going to find this area here, if it's finite, and if it's not, then we'll show that it's infinite. Okay. So is that area a finite area or not? So we're going to take the limit as a tends to pi over 2 from below of the integral from 0 to a of tan of x dx. Now, from A level, we know that the integral of tan is minus ln cos. So therefore, this is going to be equal to the limit as a tends to pi over 2 from below of negative log cos x evaluated between 0 and a. And that's going to equal the limit as a tends to pi on 2 from below of, if I plug in a into there, I'm going to get minus log cos of a. If I plug in 0, that's going to be cos of 0, which is 1, and then log of 1, which is 0. So I get subtract negative 0, so plus 0. And now if I take the limit as a tends to pi on 2, and cos of pi on 2 equals 0, and log of 0 is undefined, because I'd be trying to log 0 if I plug in a as pi on 2 into this expression. So therefore, we can conclude that this area is divergent. So this area is infinite, the integral is divergent, the integral doesn't exist. Okay, because you end up trying to divide by 0. Okay. And my fourth and final example. I'm going to find the integral of 1 over root x minus 2 between 2 and 6. So this is going to have a vertical asymptote when x is 2, because I'll be dividing by 0 at that point. So therefore, I'm going to find the limit as a tends to 2 from above of the integral from 2 to 6 of x minus 2 to the minus a half dx. And that's going to be equal to the limit as a tends to 2 from above. Oh, sorry, I missed the a again. Second time I've done that. There we go. And having carried that integral, so add 1 to the power, divide by new power, that's going to be 2 into x minus 2 to the positive a half. And we're going to evaluate that between a and 6. Okay. Limit as a tends to 2 from above of, plug in 6, that's going to be 6 minus 2, which is 4. 4 to the half is 2. 2 times 2 is 4. And then we're going to subtract 2 times the square root of a minus 2. Now, this time, again, you still wouldn't lose marks if you didn't put the plus, but this time the plus is a bit more important because you can't approach a as 2 from below, in this case, in the set of real numbers. So we should be emphasising that we are approaching 2 from above, mathematically. But you can see that when you approach 2 from above, then this square root is going to tend to 0, because this is going to be ending up being 2 times the square root of 0. So that's going to disappear as that limit takes effect, and therefore this is going to be equal to the number 4. Okay, so the answer is 4. If you were to sketch this graph, then you'd have your vertical asymptote at 2. It's there, and it's positive all the way because your positive square root, that's above the x-axis. It's going to be something like that. And then there's my 6. What we've done is we found that this area here, the area between the curve, the x-axis, and then the two lines, x equals 2 and x equals 6, that is a finite area in this case, and it's the number 4. So this area here, infinite perimeter, yes, but finite area of 4. Okay. So that's the first case of improper integrals. In the next video, we'll have a look at improper integrals which have a horizontal asymptote, and then we consider how to deal with those. Thanks very much for watching, and as always, if you've got any questions, please just drop them in the comments below.